Welcome, one and all, to video number 4, entitled Basic Soil Principles in Cal Poly ITRC's Fertigation series, sponsored by CDFA and specifically the FREP program. As always, we want to make sure you understand that there are resources available: drip micro irrigation. The Fertigation book is available both in English and Spanish, and if you take a look at this, we have a lot of free downloads, information on projects, books, equipment, and so on that you can access through the Cal Poly ITRC website. Here's a reminder about the fertigation. By the way, the Fertigation book is written primarily with a Mexican tilt to it, as opposed to Spain or that type of Spanish tilt. And we also have these free online resources. These are part of the video series. But hopefully you'll find them interesting also and educational. So what is going to be covered in this video? It's almost like a mini soil science class, except it really gets down to what's really important for you to understand. One is the cation exchange capacity, and you'll see that referred to as CEC, cation exchange capacity of the soil. Next is where and how nutrients are taken up by roots in the soil. The third one here is where in the world do nitrogen, phosphorus, and potassium go in the soil when you fertigate? In other words, you put them in through the irrigation water, so where do they end up? And then there's the idea of the available water holding capacity and how that influences the uptake of nutrients. First is the concept of the cation exchange capacity. And what we have in soils is we have exchange sites, or those are like spots where they're magnets, and they only occur on clay and humus. Now, granted, there are a few small exchange sites on sand particles and silt, but the vast majority is held on clay and humus particles. And so these very small particles of soil and organic matter, on their edges, on their sides, they have negative charges, and positive ions or cations cling to those, and they are what we call adsorbed. In other words, they're attached, but they're not integrated chemically with other ions. They're just attached, just like iron filings are attached to a magnet, or we call them fixed. So the cation nutrients that appear on the cation exchange capacity are things like calcium. Notice it has 2 charges, potassium, which has 1 charge, and ammonium. Of course, there are others like hydrogen that also are on the exchange sites, and sodium. This is a conceptual depiction of something like potassium, just as an example. First of all, if you look at the little box, it says soil colloid. That means a little piece of soil, and specifically it'll be clay with the negative exchange sites. So you see all the negatives around there. And then attached to the negatives are the positives. And so they're just like magnets again. And then you see the white potassium there in the soil water solution. And so what you have there is there's a balance always. There's an exchange between the components of the soil water solution and the components on the exchange site. Now, obviously, if the soil is very dry, you don't have a whole lot of soil water there, and the soil water isn't going very far. Keep that in mind for a few slides in the future. So the cations that are on the exchange sites aren't easily washed off or leached out. Instead, it's more of an exchange where you have a replacement of one for something that's in the soil. For example, if you fertigate with a lot of ammonium, that means the soil water solution will have a lot of ammonium in it, and it will knock off something else like a calcium or a sodium or a hydrogen that's on the exchange site and replace it. And that's the idea of exchanging. Basically there's slots there, or charges on exchange sites, and whatever dominates in the soil water solution will tend to dominate on the cation exchange capacity also. So there's always an accompanying exchange when some cation is in the soil solution is taken up by a root. That kind of leaves a spot out there in the soil water for another cation, and you get an exchange on the cation exchange sites. This illustration, depicted by the University of Georgia Extension Service, attempts to show clay particles, and you see on the edges of the clay particles are the exchange sites, and you have these little circular colored items, and the concentrations on the exchange sites again are related to concentrations in the soil water solution, and then you have contact with the root hairs, contact not with the particles here, but with the soil water, or in this case it says soil solution, same thing. So then the root hairs take things up through mass flow, if you recall, or diffusion, and then there's all this constant exchange. What happens when the root hairs take something up is typically when they take a cation up, they discharge a hydrogen ion, and that goes in the soil water solution. So there's always an exchange going on. The next idea is something you don't normally hear about at beginning levels, at least the second part of it. We know that the exchange sites, the number of exchange sites that you have, in other words, the cation exchange capacity, depends on the soil texture. Most people know that. What they're not necessarily familiar with is that it also depends on the pH of the soil. And that's what this shows. This shows a pH of 3 with just a smaller cation exchange capacity, and as the pH goes up, there's a larger cation exchange capacity. And what happens really here is the soil labs, when they measure it at a pH of 7, sort of normalize things. This slide gives you a little better idea of the concept of cation exchange capacity. Now, there are two things on this slide. One is, what in the world is it? In other words, how is the cation exchange capacity measured? And the other deals with the differences between different soil types. So let me start with how we express cation exchange capacity. This is very exciting, of course, but basically somehow it's the number of sites, or negative sites in the soil in a certain amount of soil, like 100 grams of dry soil, not wet soil. And the way we measure this is with milliequivalents, which has to be described later on, but that's some expression of charges. So we have 100 grams of soil, dry soil, and basically you measure how many charges are. And it's not that important to know the details here at this point, except if you take a look at this table, you'll see a sand, for example, has a number of 3, and a cracking clay soil down there has a number of 90. Now, in a state like California, we have the whole range. We have sands, a lot of fine sandy loams and loams, which is a 10, for example, and we actually have quite a bit of cracking clay soil. And they're completely different in terms of their cation exchange capacities, and this influences really how you're going to apply certain fertilizers. And it gets down to the importance of spoon feeding fertilizers, or many small applications. Now, if you recall from the previous slide, the cation exchange capacity is expressed as milliequivalents per 100 grams of soil. I think you all know what 100 grams of soil is, but what in the world is a milliequivalent? And if you go through these 4 notes here, first of all, every atom has an atomic weight, and I'll show you the table here on the next slide. But now, technically, the atomic weight is how many grams does the Avogadro's number of atoms hold? In other words, 6.02 times 10 to the 23rd. Very exciting. Next thing is, if you go down, anions and cations always have one or more charge. So let's see, there's the idea of a weight, and then how many charges there are. So anions and cations, and remember those may be something complicated, like a sulfate is an anion, and that's SO4, and it has 2 charges. So sulfate, which is an anion, has an atomic weight, and that's the weight of their combined atoms. So then on the bottom right here, you combine these ideas. There's a certain weight to a particle, and all the particles have different weights, and there's a certain charge. And the equivalent weight is the atomic weight of that particle divided by the charge, and it always turns out to be a positive number. Of course, we have tables for these things. Nobody expects anybody to memorize these unless you're working with it constantly, but you end up looking at this in particular when you deal with reclamation of alkaline soils and sodic soils. And when you deal with things like how much acid do you need to put in water to change the pH, it gets into these concepts. But if you take a look at this, the common constituents of irrigation waters and their weights, you have typical cations that you find in water and typical anions. And let's start with the ammonium up here. The symbol is NH4, and there's a positive charge, positive 1. And the weight of that, if you get the 1 nitrogen and then the 4 hydrogens, the atomic weight is 17. And then the mill equivalent weight is 17, that's the atomic weight, divided by 1, which is 17. And if you notice, it's switched from grams to milligrams. And that's because it's milligrams per milliequivalent. In other words, there's 17 grams in one equivalent weight, and there's 17 milligrams in one milliequivalent weight. Calcium then that's all you need is one more example here. Calcium has a charge of 2. Calcium weighs approximately 40 grams for 1 mole, or 6.02 times 10 to the 23rd atoms there. But since it has a 2 charge, you divide 40 by 2 and you get 20 is the mill equivalent weight. And it just goes on. So we have tables like this that basically tell you how much something weighs and per charge basically. So what? Well, the second bottom line is this: because sands can't store a large number of nutrients. If you notice, sand only has 3 milliequivalents per 100 grams. If you put on, just for example, a lot of ammonium, and you expect it to adhere to the cation exchange capacity, you just might be really mistaken, because there are only so many parking spaces. Whereas if you put on a large dose on clay, there may be enough parking spots, in other words exchange sites, to hold that same amount of ammonium. So you have to be really careful with sands in particular, these soils with the small cation exchange capacity, because you can flip the balance of chemistry really fast. If there's not much in the soil on the exchange sites, and you put even a moderate amount of chemical in, it can overwhelm the chemistry of the soil. In particular, you have to be careful with acids, because you can scorch a soil very quickly, a sandy soil, with acids. What happens with acids, if you really drop the pH in a soil fast, which again is easy to do with the sand, is the aluminum, you might say, gets dissolved out of the soil particles. And aluminum is very toxic to a lot of plants, and it can just fry your plants, in other words kill them, just in a matter of a day or so. So you do have to watch the chemistry, and that's one of the reasons we're going through some of this stuff here. As you recall, nutrients move into roots with 3 mechanisms, one at a time, of course. But first of all, there's root interception. That's where the root hairs, or the root, directly hits the exchange sites. Very small distance of movement there. You can imagine that if you're going to have this, you'd have to have an extremely extensive root system that's hitting all these little teeny weeny soil particles. Then there's mass flow, and that's where you have these nutrients in the soil water solution, and they're just carried along when the soil water moves towards the roots, and they're taken up as part of the ET process. And then diffusion. Diffusion is where it goes from a high concentration to a low concentration. Now, this is something that you don't talk about every day, and you might say ho-hum, but I'll get to it, why it's important to look at this. Let's take a look at nitrogen here. If you see there, the big gorilla in terms of nitrogen movement is mass flow, and that's primarily with nitrates. So it's right there in the soil water, readily available, and it moves with the water then. Phosphorus, on the other hand, and potassium, these are your two other major nutrients. They're primarily brought into the plant with diffusion. Remember, that means that you get a high concentration of phosphorus, perhaps in the soil water solution, and then as it's taken up by the plant roots, you get a lower concentration near the roots. So you get diffusion without water flow. This is just diffusion of the chemical itself in that water, and it moves towards the area of lower concentration. Calcium then is similar to nitrogen. In fact, all the others are relatively, well, the vast majority of the flow is with mass flow. So phosphorus and potassium are sort of special here. They're over here on the diffusion side. The rest of them are primarily mass flow. So the question then is, so okay, so who cares? Down at the bottom of this slide, you see where I'm going with this. Basically, with mass flow, and that's most of the nutrients here, you're only going to get mass flow if there's enough soil moisture and oxygen in the root system. Now, wait a minute, what's this oxygen doing here? Well, it turns out that for roots to do whatever they do, they need oxygen in the root zone. If you recall, up on the leaf side, up in the air, the leaves use carbon dioxide, and then they release oxygen. Down in the root system, the roots need oxygen. And so, let's see, it means that you have to have adequate soil moisture. In other words, if you're going to have mass flow, there has to be moisture there. But you can't have too much, because if you have too much moisture in the soil, you're not going to have any oxygen. There's no air down there. So there's going to be a balance. So here we get the nutrient movement tied to irrigation water management. The same thing goes in for phosphorus and potassium. Granted, there's a bit of a difference in the way the particular ions move to the roots. But the bottom line is, whether it's mass flow or diffusion, that's through the water. That's the chemicals are in the water, and they move to the roots somehow. Now, diffusion is a real localized thing. It's only going to be a few millimeters. And if that means then that you have to have a really good, healthy, extensive root system, if you have nutrient problems, if you're not taking up enough phosphorus, if you have a deficiency, in other words, what this says is that it may not necessarily be because you don't have enough phosphorus in the soil. It may be that you don't have a good, healthy root system. Take a look at this. If the phosphorus and potassium are only going to move a few millimeters, you just have to have a good, healthy root system, and then you have to have that root system where the nutrients reside, and you have to have moisture. That's quite a combination. So let's get to the bottom line here. Basically, you're going to try to apply water uniformly with a good DU. Therefore, your fertigated chemicals will go out with a good DU. But now we're talking about, okay, how often should you apply things? And let's see, where are those nutrients in the root zone? And the bottom line is, there's little or no nutrient uptake unless there's sufficient soil water in the same zones as the nutrients. So now you have to say, well, where are these nutrients? And we go on from here. Here's the important thing. Most of the phosphorus and the ammonium are in the top foot of soil. So the top foot of soil needs to be moist for optimum availability. It's kind of interesting with the phosphorus. If you do land grading and you cut the top part of your root zone, basically what you're doing is removing most of the phosphorus from that area of the field and putting it somewhere else. And that discrepancy in phosphorus availability associated with where you do cuts and where you do fills with land leveling will persist for years and years. It doesn't just naturally heal itself. So you may want to take a look at that if you're dealing with a field that has been land graded. With fertigation, if you put the fertilizer on evenly, it doesn't offset these imbalances that may reside in the soil due to land grading. So one of the ideas is what you do is you try to eliminate those inherent differences in fertility throughout a field first, and then what you do is you fertigate uniformly and you're good to go. But back to this thing here about phosphorus and ammonium in the top foot of soil and it being moist. With surface irrigation, as you know, those irrigations are only applied once every week and a half, once every 2 weeks or so, typically. And what happens there is if you take a look at the water uptake rates in different parts of the soil, you get a very large amount of the water that's taken up either evaporates or goes into the roots from the top foot or so of soil. So it gets really dry. If you walked around in a field, you can kick the soil and you get dusty. That's called very dry. In fact, it's called air dry. Not a lot of nutrient movement. So bingo, you associate that with on the left here, and you say, well, gee, if I have ammonium and phosphorus in the top foot and I'm drying out the top foot of soil, I guess I'm not getting a whole lot of uptake. And that is indeed the case. Now with drip or micro irrigation, it's possible to keep the top foot relatively moist all the time. And this probably explains some of the important yield improvements that we've seen with drip and micro irrigation. It's granted, there's the nice thing about water availability is sometimes we look at water just as if it's a separate thing, but when you combine it with this idea of fertilizer management, it really makes sense. You might say that a corollary here is this. Okay, the nutrient movement, virtually all of it, into plant roots is via soil water, whether it's mass flow or diffusion. So it makes sense to apply fertilizers to the irrigation water because they'll be together at the right spot. Now, when I say they'll be there at the right spot, well, maybe so and maybe no. We have to talk about how fertigated fertilizers move into and through the soil. So these are our most common ones that we use, not counting the micronutrients. We have nitrate, urea, and ammonium. Those are the primary forms that are found in fertilizers. Then we have different phosphates and potassium. They're obviously associated with other things, but these are the main ingredients here. If we look at nitrate movement, it's an anion, and because it's an anion, it's not going to be attracted to the cation exchange capacity. And if you recall, it really doesn't combine with other cations, not other cations, but with cations to form insoluble compounds. In other words, nitrate's really quite soluble. So it moves with the irrigation water. And that means if 30% of the irrigation water depercolates during an irrigation, well, 30% of the nitrate you applied with the water also depercolates because it's just moving along with the water. It also means that nitrate is going to move throughout the root zone with the water. As you apply water, if you're applying nitrogen with that, or nitrate nitrogen, then it moves wherever the irrigation water goes. It doesn't just stay at the surface of the soil. Ammonium, on the other hand, when it's fertigated, is quite different. First of all, it's a cation, and because it's a cation, it's attracted to the cation exchange capacity and relatively quickly. Most of the fertigated ammonium is absorbed really in the top foot of the soil or so. And plants can take up ammonium, and this is one of the reasons some growers, especially with produce crops, lettuce, broccoli, and so on, will apply ammonium early in the season because for early crops, it turns out that ammonium can be taken up relatively easy if it's readily available. But most of the ammonium that we apply as fertilizer eventually converts to nitrate over time. And just because it's nitrate doesn't mean it's moving in the soil water. There has to be soil water moving in order for the nitrate to move. So it'll be remaining at the same location where the conversion took process. And but when you irrigate the next time, some of that nitrate will be carried along with irrigation water that's moving down to the root zone. Urea is the third form of nitrogen fertilizer that we use a lot of. And it has no charge, so it's not attracted to the cation exchange capacity, and it moves into the soil with the water and it goes down, more or less like nitrate. And then after a while, what happens is the urea that ends up down in the soil profile, or the root zone, is converted by an enzyme, and it's called the urease enzyme. And as a result, you find ammonium distributed throughout the root zone rather than only at the top. So this is one way to get ammonium throughout the root zone. Now there's a delayed process here. In other words, when you do a urea application, it isn't available immediately to the plants. But then it converts to ammonium, and plant roots do take up some ammonium. And it's throughout the root zone, not just at the very top. And then eventually you'll have microbial action, which converts the ammonium to nitrate. And that will happen wherever the ammonium is in the root zone. Now, phosphate's kind of interesting. First of all, it's an anion, so you'd say, well, it must stay in the soil water, just like nitrate. Well, that's not right. And even though it's not absorbed or adsorbed onto the cation exchange capacity, it's actually very immobile, especially in western soils where we have a lot of calcium and magnesium in the soil and in the water. What happens is it's attracted to calcium, magnesium, or vice versa, and it makes a rock. And they're just, these rocks, calcium phosphate, magnesium phosphate, they're just sitting there in the soil, not on the exchange sites, but they sure don't move. And that happens real quickly. So that's one reason most phosphate fertilizers are on the top foot of the soil. And what happens with the native phosphates that were in the soil, they're taken up by the roots. They go into the leaves fall down on the ground. Those phosphates then that were in the leaves stay on the top of the soil, and that's why they gradually concentrate in the top foot of soil. So I've mentioned nitrogen and phosphorus, and now there's potassium. These are the big three. And it turns out that a lot of soils have a lot of potassium in them. But here's the kicker on this one. There's something called the potassium release rate. And in other words, you can have a lot of it, but it may not be released by the soil very quickly. It's kind of like having a little hole in a big tank. You have a lot of water in a tank, but it isn't coming out very fast. It isn't quite that way, but that's the general idea. And so what happens is you can have this big reservoir of potassium, but the crops sometimes need very large amounts in a short amount of time at certain growth stages. And so potassium fertigation is very common, and it basically supplements the high potassium that may already exist in your soil. It's a matter of release rate. So it's a cation. It acts like ammonium, that it's absorbed onto cation exchange capacity. A big difference here is that it is not like ammonium because it doesn't convert to anything else. In other words, it doesn't change to the equivalent of nitrate. And it just stays on the exchange sites where it was first adsorbed until later on, it gets in the soil water solution, and there's that exchange process, and it gets into the plant roots. So let's see. What I've talked about here in this particular video so far is that you have different fertilizers, different forms of nitrogen, and there's potassium and phosphorus. And they end up in different places in the root zone, and you want to put them on evenly. but now it does help to have a little better understanding of this whole thing of irrigation water and movement and retention in the soil. So I'm going to go through a few basic concepts of water contents in the soil. What we have here is a simplistic illustration of important soil water contents. And there are a lot of ways that people depict this. But what we have here on the left is percent of soil voids filled with water, and that refers to the 100 to 0. For example, if you have an oven-dry soil where you actually take a sample of soil and you put it in an oven and essentially you boil off all the water, there's 0% of the voids, that means holes or pore spaces. 0% of the voids are filled with water. Now, if you look at this right here, it says about 6 inches of pore space are available per foot of soil. What does that mean? That means if you took an undisturbed sample of soil and you were somehow able to, and we have ways to do this, you were able to figure out what percent by volume is solids. You'd find that about 50% of the volume is solids and the rest is pore space. That pore space can be occupied by air or water. And if it's 50% of the space is solids, that means 50% is pore space. 50% of a foot is 6 inches. So that's a terminology here. So this means half of the pore space, half of the depth is really occupied by pores. Now it's a question of how much of these pores is filled with water. And oven dry means nothing. Then we have air dry. It's not quite as dry as oven dry. And don't worry about, whether this is 5% or 6% or 3%. This is conceptual here. Moving up here, if you get a little water in the soil, you have a point called permanent wilting point. And this is a point where, in theory, that's the lower limit of water availability for plant uptake. This is not storage, this is uptake. In other words, this water here is not very extensive in the soil at this point. It's held real tightly by the soil matrix. And the plants, well, it just doesn't move. It's held so tightly in the soil, it doesn't move easily into the roots. And so it moves so slowly toward the roots that the plant will permanently wilt. In other words, it'll die. Now, of course, this is for a particular point in the root zone. The whole root zone does not arrive at permanent wilting point. You get gradations, you get different amounts of drying out and wetting depending on the depth you are in the soil. Up here, this is field capacity. You can think of a sponge. You can get it all full of water and you hold it in the air and water drains out. And the moisture content that the sponge has, or in this case the soil has, after free drainage, after free drainage is stopped, is called field capacity. That's the amount of water that's left above 0. So what we have is this idea of available water holding capacity, or storable water. And the upper limit is how much can the soil store against gravity. And the lower limit is, well, there's still a lot of water left, but the plant really can't take it up fast enough to keep living. So that's what we call storable water. Granted, this is storable water down here, but it's not usable water down here below permanent wilting point. So anyway, this is a zone we work in, and by the time you get down to here at permanent wilting point, if the plant's dead, that isn't doing you much good. So we typically try to operate with a root zone, and most of the root zone up here somewhere, closer to field capacity. Now, a lot of people think that when you irrigate, you saturate the soil, but that's not the case, except on surface irrigation. And then, of course, some drip irrigation, you have water standing on the top of the ground, when it doesn't go in. But saturation means that all the voids, all the pore spaces are full of water, which means then, if you flip it around, it says if there's all full of water, there's no air, which means there's no oxygen. That's bad news for plants. Now, the saturation may only occur at the surface, or it may occur, like in a rice field, it may occur all the way down the root zone. Now, here's an interesting thing. This is what most people don't quite get here, is when you irrigate, even with furrow irrigation, granted, right there in the furrow, it may be saturated in the top few inches, but you go a little deeper and the water content is not there except on a real heavy clay soil. It's lower than that, but it's above field capacity. What this means is that there's still oxygen in the root zone up here. See, there's this gap between this water content and here. There's still oxygen in the root zone. If you know, when you irrigate, the plants are still respiring. They're doing just fine. There has to be this oxygen here. And then the water is above field capacity, which means if it's at this level, it's draining through the soil. It's going through the soil. It's proceeding down further. So it's above field capacity, lower than saturation. The exact location here depends on the irrigation method, like how fast you're applying the water. With a very light sprinkler irrigation, it might be right here, for example. With surface irrigation, it might be a little higher here. But this is where you are here, and then once you stop irrigating, this water content drops to field capacity, which means that this water goes below that next layer of soil. So again, we have different names we call things. Oven dry is just dry. Air dry is pretty darn dry, but there's dust, but it still has some moisture in it. Permanent wilting point has more moisture, but it isn't doing the plants much good. Field capacity isn't the upper limit of water use. All it is the upper limit of water storage. In other words, the water up here above field capacity can be used by the plant, but it can't be stored. Then you have this idea that the soil is not saturated when you irrigate, except in some cases, and then this is like you're in deep trouble up here when you saturate everything. So that's at least one depiction of water concentrations. Now this is another depiction of soil water. See, people think of soil water in different ways. Some people say, well, how much water is in the soil? And that's how you have to think about it in terms of how much do I have to apply. You're talking volumes of water, inches of water. But a lot of our sensors, or some of the sensors, like soil moisture sensors, say, well, how tightly is the water held? That would be something like a gypsum block or a tensiometer, for example, or one of these watermark sensors. So there are different kinds of sensors. Some measure how tightly the water is held. Some, like capacitance meters, will measure more the quantity of water, but not how tightly it's held. So that's just to get everything confusing. What I have here is two different graphs, or two different scales. The one on the left is matrix potential. So we have the matrix potential is the measure of how tightly the water is held by the soil itself. And there's a zero potential at the water table. And then you see this negative number. That means that, boy, it's being held tightly. Don't worry about the negative. It's like this. When it's down here, boy, that water is being held very tightly. If you notice at permanent wilting point, there's negative 1500, and okay, this is kilopascals or joules per kilogram. Or if it's just 15, that's bars. But anyway, it gets held more and more tightly as the soil gets drier. So remember that this is the storable zone. But certainly plants can use water in this zone up here above field capacity because it's held lightly. It's just that there's water moving down in this zone right here because it's above field capacity. So this is our available water holding capacity. And this is a little symbol here, moisture content by volume. And see, this says 50%. So that's kind of our typical textbook loam soil that has 50% pores in it. So it's just another idea. In other words, some people think of tension or suction and some people are thinking in terms of quantity of water. But in both cases, we do talk about field capacity, permanent wilting point, how far down should you let this reservoir go. You don't want to go too far down. You want to stay up here. So how do you keep it, reasonably moist without putting water down the tubes by over irrigating? So this is kind of a key idea that people don't quite understand. I hear people say, well, the water is pushing something down in the soil. Well, it doesn't quite work that way. Think of it as water moving kind of a thin horizontal lens at a time. What happens is the water has to get to field capacity in a lens. If you notice this lens here, the soil lens. So you have to get to field capacity before you have to raise the soil to at least that level of moisture before it will pass through a lens. And as I mentioned before, it'll be up somewhere somewhat higher. This water then is moving. You might say that this water down here is not moving. It's back hidden away in the smaller pores. That's not exactly right, but it's close to being right. So this is the water that's moving on down. It's your irrigation water. But the idea is you're not going to get any movement downward until a particular lens first fills up to field capacity. This is a depiction of how water moves into a soil during an irrigation. What you have here is a soil surface, and these are very thin layers. Just imagine this is an inch thick, something like that. Here's another layer an inch thick, and so on. And what happens is the water won't go below 1 inch until first it gets to field capacity and exceeds field capacity. Then water goes down to the next inch, just inches just for illustration. And it fills that up to field capacity and then goes, once there's more water coming in than that, it goes down to the next one. In other words, it isn't being pushing through. It's filling up the pores, and once the small pores are filled up, water just keeps moving through the larger pores. That's all it is. It's not pushing anything through the small pores. This image down here, the fourth one, shows a very thin layer that's maybe quite a bit lower than field capacity at the time, but it's filling up. It'll get to field capacity, and then if water continues to come in, that extra water will go through the large pores. It'll continue through the large pores and go down to the next layer. So it's one layer at a time. That's how the water actually moves into the soil. So again, to repeat, what happens is water infiltrates vertically into a soil. It does not move like a piston. And it first fills up the soil pores in one thin layer to some level above field capacity. Any extra water goes through the large soil pores. And then there's always some mixing, of course. There's some water as it's going, let's say, the large pores are kind of like a super highway, and then the small pores are off on the side. And you can imagine if the wind goes by, there'll be some mixing, It's not like this water's moving fast, but there's always some mixing and diffusion between the water in the big pores and the little pores. And it's not like no water moves downward through the little pores, but so there's some mixing. And so, for example, if you had some nitrate in the small pores and you irrigate, some of that nitrate that is stored in the soil will mix with this new water, the new irrigation water, and combine with whatever nitrates in your new irrigation water, and it'll continue to move down and leach. But it's not as if there's a piston that removes all the nutrients every time you irrigate. Not that way at all. This is a reiteration of an idea that in most soils during an irrigation, the water it doesn't saturate the soil. And so you do get, of course, roots needing oxygen. Where you really see the saturation problem, especially is on the ends of alfalfa fields, where they get what's called scald. And if the water's just sitting there, you'll find that the alfalfa just dies back. That's probably one of the most obvious situations that I can think of. This idea number 4 is again a reiteration of what I said before, but it's maybe it bears repeating. There's a limit to how much water can be stored in the soil, and that's going to depend on the soil type. Sands cannot store as much as as clays, for example, they don't have as many fine pores. In other words, the water level or water concentration at field capacity is really defined by the texture of the soil largely, and if you have a lot of very small pores like in a clay soil, the amount of water held at field capacity is higher than for a sand. But once a soil profile reaches field capacity, any additional drop is going to go on through the large pores and depercolate and carry some nitrate with it. This right here is just another illustration trying to get the idea across of what's going on out there. It says, as the soil layer dries out, the remaining water in that layer is held increasingly more tightly by the soil matrix. Now, what in the world does that mean? If you look at that, if you look at the soil particles, they touch each other in places, although this doesn't show that. But that's called the soil matrix. It's a combination of soil and water and air. And what you see is that as the soil dries out, this interface here, let's take this one. This is a kind of a good example here, right here. What happens is this soil dries out, this interface right here scoots down into smaller and smaller openings, as you might see it. And it turns out there's this phenomena called surface tension of soil. You've seen little bugs moving along on the top of water. I should have said surface tension of water, not surface tension of soil, but you see those little water bugs scooting along on the top, or you maybe have even tried to float a razor blade on the top of water. There's this water tension. We depict that over here as capillary rise. If you've ever seen a capillary tube, it's a real thin pore, and if you put a real thin tube right here, a thin tube like a glass tube in a container of water, the water rises up quite a distance. If you put a big tube in the water, it doesn't rise far at all. In fact, it may not rise any at all. You know, we call this the meniscus often, if you've had any chemistry and you've looked in graduated cylinders. But this rise, in other words, the rise, see, that indicates the suction, obviously. It's dependent on the physical property of water called surface water tension, and then it's related to the radius of the capillary tube. So basically this says with a small tube, there's a lot of negative pressure. In other words, it really sucks it up a lot. If this interface occurs over here, where there's a small radius, which occurs when the soil dries out, this water is held by this matrix much tighter than if there's a large interface right here. And so it isn't anything magical. It's just as there's less and less water, the water retreats into the small pores, and it's just a physical property of water that is held more tightly with a smaller radius of curvature right here. So the result is the nutrients are in this water, the remaining water in these small pores. See, these have drained out, or they've been emptied out. The nutrients are in here, and as the soil gets drier and drier, it just isn't moving very freely over to the plant roots. So just a continuation of that idea, in other words, is that as the soil dries out, the movement of the water and nutrients is increasingly restricted as the soil dries out too much. So you want that balance. You don't want so much water in there that it's draining out. In other words, you don't want to irrigate too long, but you want to irrigate frequently enough and with the right amount, so you don't put too much on, but you keep the soil, in a decent condition. That is, if you don't want to stress the plant. Keep in mind, sometimes you want to stress plants. So you're interested in fertigation, you have to be interested in irrigation also. The water management is tied to fertilizer management. As I keep saying, too much irrigation water during an event causes nitrates to depercolate, which is a waste of energy, a waste of money, and a degradation of the environment. But infrequent irrigations or insufficient irrigations restrict fertilizer uptake into the roots. Now these are different things here. There are several ideas here. Too much irrigation water during an irrigation event can occur with infrequent or frequent irrigations. It's entirely possible to have infrequent irrigations where the plants get stressed, and then you put too much water on during the next irrigation, or vice versa. There are all kinds of combinations. So basically, you want to have the right amount of water at the right time. That's what it gets down to. And for that, you have to understand something about your irrigation method. To illustrate this, I'm going to bring out drip irrigation here. With trees and vines, it's common to only wet about 40% or so of the soil volume. In fact, there are a lot of drip irrigated trees and vines with considerably less than 40% of the volume. And then because of this or that, whatever reason, farmers may get it half right. They may take a look at evapotranspiration information and how much water a plant needs in a week. And amazingly, there are farmers who irrigate crops like this. This is a pistachio crop. They only irrigate once a week or so. And they put on a week's worth of water. Now here's the problem. Remember, there's a water holding capacity. And you don't have much water holding capacity here simply because you don't have much soil that gets wet. So it doesn't take a whole lot of water to fill up the, let's call it the reservoir, in the small amount of soil that's getting wet. So what can happen is, I see this a lot, is people put on the right amount of water per week, but they put on too much at once. And so what happens is they get deep percolation, and then that small root zone dries out because there's just not much water stored there. And so the plant gets stressed before they irrigate next time. And isn't that quite a kicker? In other words, you have both stress and over irrigation, even though they put the right amount of water on, just not quite correctly. So there are a number of reasons people do this. One is, you look at the top of the soil and you don't really see what's going on underneath. But the other reason is for labor reasons. People just find it more convenient to irrigate once or twice a week. This doesn't mean you want to irrigate every day out of the week, but you have to have the correct balance. That's really what it's saying. So you might want to take a look at that if you're managing a drip irrigated orchard. So this concludes video number 4 in our series of 24 or 25 videos, and hope you enjoyed it and move on to the next one. See you then.